Good afternoon and welcome to this week's Focus on Geothermal presented by Think Geoenergy and Enerchange. My name is Marlene and I'm pleased to welcome Agathe and Nicolas from TLS Geothermics. Agathe holds a master's degree in geophysics, geology and earth system dynamics. Since 2024, she has been working as a geophysical engineer at TLS Geothermics in Toulouse. Her colleague, Nicolas, also holds a master's degree in geology and one in earth dynamics. He also went on to complete a PhD in earth science. After his PhD, he joined TLS Geothermics as an exploration geologist. He is responsible for the company's projects on Martinique Island in Germany, as well as for prospection in the US. In today's presentation, Agathe and Nicolas will speak about the transdisciplinary approach as an innovative tool for geothermal exploration in basement-hosted crustal fault zones with a focus on Saxony, Germany. TLS Geothermics has developed a specialized geophysical method to quantify the geothermal potential of such zones as part of its systematic exploration workflow. This workflow is based on the joint inversion of three passive methods: gravity, passive seismic, and magnetotelluric data. Each method provides complementary information on density, resistivity, and seismic velocity models in the crust. In combination, these methods can be used to efficiently quantify the geothermal potential and to identify targets for the first exploration wells. We look forward to an insightful presentation. But quickly, before we start, I just wanted to remind everyone of our IGC, which will come up in June. So in case you haven't registered already, feel free to check it out. But for now, Agathe and Nicolas, the floor is yours.
So hi everyone. So today I will show you our transdisciplinary approach to explore a geothermal system in basement-hosted crustal fault zone. And we will focus on our current project, Saxony, Germany, but we will also use some results from our past project in the US and in France. So this project in Saxony is co-developed by TLS Geothermics and by Calliosphere. So before we jump in, I will say a few words about TLS Geothermics. So we are a geothermal developer. Our goal is to find hidden blind geothermal systems. And we develop operation method inspired from the oil and gas methodology. And we also develop our own numerical tools and machine learning models to find this hidden system. So we have several projects worldwide, 4 in the USA, in the Basin and Range in Nevada, 2 in the Caribbean island in Martinique, and 2 in Europe, 1 in France in the Massif Central, and our project in Germany. So this project is located in Saxony, in eastern Germany, close to the border with Czech Republic. So you can see here the limit of our lease in white. The southern part of the lease is actually the Czech border. So this lease is located in the Grundgebirge Massif. And here to the south of the lease, we have the Eger Rift, which is a Cenozoic rift system. And so for this project, we target both heat and power usage. We expect 35 to 45 megawatt thermal with one single doublet, so which is equivalent to roughly 5 megawatt electric. And we also expect lithium-rich brines, because the basement in this area is composed of lithium-rich carboniferous granite. So yeah, so we expect lithium-rich brines. The target is fault zone. We define this area as an area of interest based on our crustal fault zone concept that I will explain right now. So the concept is actually quite simple. You need a crustal fault zone, means a fault that affects the entire brittle crust. And this fault need to be well oriented in regard to the stress field and in favorable lithologies to be permeable. And if it is permeable enough, you will have free convection cells that will develop along the fault. And the fault will in fact act as giant heat exchanger between the surface and the depth. And so you will have cold water downflows along the fault and warm water upflows along the fault. It's what is represented here. You have here the downflows with the isotherm deepening, and here the upflows with the isotherm shallowing. And to identify this specific context, we have three main criteria, geological criteria, that help us define a lease. The first one is a drain, so the presence of a crustal fault zone. So we need specific structural context, faults that are oriented favorably to the stress field, and favorable topologies, because a fault in shales behave the same than a fault in a granite. Although we are looking at blind system, any type of thermal anomalies on the surface can help us target specific interesting area. So that's the second point they hit. And the last one is the fluid. Again, any evidence of deep mantle gas degassing to the surface, or any evidence of hydrothermal alteration or contamination of groundwater by some type of hydrothermal fluids can also help us targeting a lease and also reducing the risk when we define a lease. So when we do our exploration, we start from the large scale, and we try to find, using machine learning and also our own expertise, areas where we can meet these three different criteria. And then if we find the zone, so this is, for example, the Grundgebirge Massif, we try to identify prospect scale areas that are also meeting these three criteria. And if we find them, we ask for an exploration license and do all the exploration process to de-risk and decide if we want to drill in the end or not. So we'll review briefly all the different criteria that help us deciding this area in Saxony was interesting. So the first about the drain. The area is composed of carboniferous granites in red here. And on the eastern side of the granites, we have high-grade gneiss. And on the western side, we have low-grade mica schist, but we expect below this mica schist the same gneiss. So the lithology is quite favorable for having open fractures in the basement. Now we have three main orientations for the faults. The first one is northeast southwest, as you can see here, and it is parallel to the rift faults. And then we have a northwest south-southeast orientation and a north-south orientation. For a fault to be permeable, it has to be parallel to the main horizontal stress axis. So this is what you can see here. The north-northwest south-southeast faults and the north-south faults are roughly parallel to this sigma H max. So they're quite well oriented. And in this area, the tectonic regime is dominantly strike slip. So this is also favorable for permeability along faults. Now, if we look at the thermal anomalies, this area is not anomalously hot, the European scale, but the granites are quite radiogenic. And we have also local thermal anomalies, as you can see, for example, here, with really low heat flows and really high heat flows on a short distance. You can see the same pattern here, actually a line along the fault, and same here. This usually indicates possible convection cells because you have the low heat flows that are related to the infiltration of cold water in the basement and the high heat flows that are related to upflow of warm waters. So this is not conclusive evidence, but it is an interesting observation. And finally, for the fluid, we don't have any evidence of fluid circulation at the surface in our lease, although we have several hydrothermal alteration along some fault zone and fractures that can indicate that there was recently fluid circulation. But on the southern part of our lease in Czech Republic, there is a lot of evidence of CO2 degassing and actually mantle-leak CO2, and also several thermal springs, for example, this one. And the estimated reservoir temperature for the water from these springs is around 140 degrees. So again, interesting observation. So based on this first screening, we decided to take an exploration lease. And following this work, we started designing the geophysical survey to explore this area. So we use three different methods, the passive seismic, magnetotelluric, and gravity methods that Agathe will explain in detail right after. And for the passive seismic, we just finished the acquisition actually. The survey is quite dense in the center of the lease where we think there is the most potential. And the nodes on the border of the lease, they're used to image deeper because basically the wider the network is, the deeper you can image. For the magnetotelluric, we will do the survey in May or June. And the network is dense in the center of our lease. And finally, for the gravity data, there was already a lot of existing data, so we managed to have access to this data and we reprocessed them. After the design of the survey, we pass to the geophysical acquisition and modeling. And now we'll let Agathe.
Yeah, so as Nicolas said, at TLS we use mainly 3 geophysical methods in our workflow. All of these methods are passive and non-destructive, and each one is sensitive to different subsurface parameters and us to better constrain subsurface structure. But as the acquisition of data is still in progress in Saxony, I will use the results obtained in other areas to illustrate my presentation. So the first method in our workflow is the gravity method. With this method, we measure the absolute gravity, but the absolute measurement taken at the surface are sensitive to many factors, such as, for example, the position of the point on the globe surface. And so we make some measurements, and then we can have the free air anomaly that is sensitive to topography and to the structures beneath the measurement points. But the gravity method is more sensitive to masses of rocks close to the measurement points. And so the free air anomaly is highly correlated to topography. For example, on this map taken from measurement made in the French Massif Central, we can see that the chaîne des puits clearly stands out. So in the next step, we want to correct the topography effect to keep only the effect of the structures beneath the points. And doing this correction, we obtained what we call the Bouguer anomaly. The shape of this anomaly profile can give us a lot of information about the subsurface structures and their shape. As you can see on this scheme, for example, bell-shaped curve indicates more or less ball-shaped dense body in the subsurface. And for example, a fault is more indicated by this type of profile on the anomaly. The second method that we use is magnetotellurics. It is an electromagnetic method, and it is based on the Earth's magnetic field variations, mainly through solar wind. This magnetic field, by the induction effect, electric currents in the subsurface, and these electric currents in turn generate secondary magnetic field. At the surface, we deploy empty stations that can record both of the fields simultaneously. Then for each of the stations that we deployed at the surface, here it's an example of a network deployed in the French Massif Central. So for each of these stations, we can obtain what we call an impedance tensor. And this impedance tensor characterizes the variation of resistivity. It's like a simplification of the structure of the subsurface. And all the curves are plotted as a function of frequency, because frequency is proxy for depth. Lower frequencies are sensitive to deeper structures. Here, on this example of impedance tensor, we can see that we have 2 different types of curves. We have phase curve and apparent resistivity curves, but we focus on the apparent resistivity that represents a kind of average of the structures beneath the measurement site. Then, with all the tensors obtained at each site, we perform what we call a 3D inversion. The aim is to obtain a 3D model of resistivity that best explains the data measured at the surface. So here it's an example of a model obtained from measurement made in the French Massif Central. On the left-hand side, you have some horizontal section, and on the right-hand side, you have a vertical resistivity profile. On both of these figures, weaker resistivity are represented with a warm color because they are often associated with warmer structures in the subsurface. We can also see that near surface structures are modeled in greater details because the model resolution decreases with depth. So the last method we use in our workflow is passive seismic. In passive seismic, we focus on ambient noise. Here, for example, you have an example of station network deployed in the French Massif Central. And at each of the stations deployed, we can obtain this type of trace. The simplest way and the most visual way to represent this data is to plot what we call a spectrogram, a graph representing the amplitude of the signal as a function of time and period or frequency. Here, for example, you have 1 month of data, and the black colors indicate the lower intensity of signal. Here, typically on this graph, you can see the variation between day and night. So, to the passive seismic data that we recorded, we can apply some processing methods. So the first that we use is called H over V method. It's a method more used in sedimentary context, and it can give us the thickness of a sedimentary basin by calculating its resonance frequency. The resonance frequency represents the frequency for which the spectral ratio of the vertical and the horizontal components of the spectrum is the highest. So here it is shown by the red line. And then we can repeat this calculation for all the stations in the network, and we can derive a map of the thickness of the basin, like this example obtained from measurements recorded in Nevada. The second processing method that we use is called ambient noise tomography. And this one focuses on only on noise and not earthquakes. In this method, we are particularly interested in the surface wave because they have a dispersion property on which the method is based. The dispersion property means that different frequencies travel at different velocities and sample different depths. And similarly as MT, long period surface waves are sensitive to higher depths. And then this method consists of comparing the noise recorded at each station of a station pair. This comparison gives us response of the medium between the two stations. And then by analyzing this response with a spectrogram, we can derive a dispersion curve that represents the evolution of phase wave velocity as a function of frequency. Then we repeat this for all the station pairs in the network, and we can obtain a map of the average surface wave velocity between each station pair. In the last step, we do an inversion as in MT, and the aim is to obtain a 3D velocity model that best explains the data measured at the surface. So all the methods I have presented so far have different resolution and are sensitive to different parameters. But at the end of the geophysical process, we would like to have models that can explain the different parameters to each other so that they are better constrained and more realistic. To do so, we carry out joint inversion between MT, gravity, and passive seismic data. For gravity data, we use Boolean anomaly residuals. For passive seismic data, we use dispersion curves and velocity model. And to avoid an excessive computation time, we use resistivity model from MT data, but it is only used as a constraint in the inversion and remains fixed in the process. And then by correlating these parameters using physical laws, the inversion is able to find a velocity model and a density model that best explains the various parameters measured in the surface. And here you can clearly see that, as said before, the resistivity model remained constant in the inversion. Recently, we have developed another tool for processing seismic data. This time it is not based on ambient noise, but on the seismic events recorded during the acquisition. And thanks to deep learning algorithm and the velocity model derived from joint inversion, we can detect and localize in time and space seismic events. Here it's an example of what we obtained from measurement made in French Massif Central. And then with these results, we can derive focal mechanisms that give the orientation on the direction of rupture that triggers the seismic events. The tool allows us to understand how the faults move in the area.
So now that the geophysical work is completed, it's time to do the final quantitative geological modeling to extract some key parameter to assess the potential resource. So the idea is to use the result from the joint inversion model, so the resistivity model, the density model, and the seismic wave velocity model, to extract geological parameters such as the porosity, the temperature field, and the fluid composition like the salinity or the content even in gas. To the link between the geophysical model and these geological parameters, we use petrophysical models. So basically there are semi-empirical and theoretical laws that link some geophysical property to this parameter. So for example, laws linking the fluid conductivity with the salinity and the temperature of the fluid, laws that link the seismic wave velocity to the temperature, etc., etc. So there's quite a lot of different laws. And so the idea is to fit this parameter temperature porosity to best explain our geophysical results. So in the end, we will have for each cell of our geophysical model, we will have mean and spread of the different parameters. So porosity, temperature, fluid composition, and you can also add other type of parameters. The more parameters you add, the more complex the model gets. And the idea is to use these parameters to estimate the power production and to also target the wells. So this is the result actually of this geological quantitative modeling or geological inversion, you can call it as well, for our project in Massif Central. And the idea is to do the same in Saxony in the end. So here, this colored surface is the 150 degrees isotherm, and the color corresponds to the porosity along this isotherm. We removed all the faults in this 3D model for clarity. And so what you can see is that isotherm is not flat, but actually it has topography. And where we have the shallow isotherm, it's where we have the fluid upflow, and it is actually located along fault intersections. And so this helps us actually targeting the wells. So obviously we will drill where the isotherm is the shallowest and where the porosity is the highest, including also some surface constraint for the location of the well. And with also this temperature field, we can estimate the power capacity. Indeed, for each cell of our model, we will have a probability function of the heating place, so a mean and standard deviation of the heating place that is derived actually from the geophysical models, and from this heating place, using also the other parameter associated to the type of power plant that we want to use, etc. We can estimate in the end the power capacity and assess in the end the economicity of the project. To conclude, the combined anti-gravity and passive seismic data or a low-cost geophysical survey, non-invasive techniques. So this is a really important point, especially where there is in areas where there are problems of social acceptance. And finally, these tools are actually designed for exploration of crystal fault zone. It helps us constrain the fault model, refine the crystal stress field, that is a key parameter for the permeability of the fault, and help us quantify key parameters to assess the economicity of the project. To conclude, it increases the chances of success at a lower cost. So thank you for your time.
Thank you.
Yes, thank you to Agathe and Nicolas for the very interesting presentation. We also already have a lot of questions coming in, so I'm just going to go ahead and start with the first one. Actually, I think it's two that are rather similar, so I'm trying to connect them. So the first one would be, are there any other post-drilling petrophysical survey techniques that could augment these techniques? Static seismogram, bulk density from the wellbore, core sample correlation. And then there's another person that's asking about the petrophysical models, and she's writing that the presented geophysical models will have a rather low spatial and depth resolution, and how you want to connect it with the petrophysical models. So maybe you can combine the answers to the two.
So for the first question, any type of borehole diagraphy and petrophysics can be useful. These tools are actually, we use these tools prior to target a well, but then from the result of the wells, you can use the borehole diagraphy and petrophysics to refine our tool and to improve it. That's how we see it, because this tool is used in the exploration phase, so prior to drilling, but the result of the drilling can help us refine our process and our tool. That's how we see it.
And then for the resolution of the model, actually it's not this one.
At lower depth, the resolution is quite good, but obviously the resolution is way lower than the fracture that we are targeting. So the result of our model, they won't tell us exactly what type of fracture we want to intersect, but they can tell us more or less the area and depth where there is some type of an anomaly in the temperature field or in the porosity. Then to reduce the risk, the thing is that we are targeting fault zones. So that's actually a key parameter, is to have like quite well constrained fault model, because then if we drill through the fault zone in the area that we identify as favorable, there is a lot of chance that we will intersect faults and fractures. That's how we do it. And we are also developing, but that's still under development, other geophysical tools to try to monitor the fluid circulation in the subsurface more precisely, and maybe to be able to target more precisely our well and our target. But that's under development for the moment.
All right. Could you maybe also provide more detail on how you want to link geophysical data to flow rates at target temperatures based on analogs with the same data set in operating fields?
The temperature, one of the key parameters will be the seismic wave velocity, that are in part by the temperature, but also by the fluid content. All those parameters that you have to fit together, so it's not easy process. For the flow rate, it's harder because we don't quantify directly the flow rate. We have the heat in place, so we have a power capacity. Basically, it is to assess it, we use the heat in place, so it's the amount of heat that we have in a given volume, and then we use a recovery factor. So it's basically a percentage of the heat that we could extract. We have a probability function of recovery factor that is based on the bibliography from several geothermal fields in the world. That is really difficult to assess, but we are trying to have a really conservative approach on this and use quite low recovery factors to not oversell the project. That's how we do it. For the moment, we don't directly estimate the flow rate. We use a recovery factor to estimate the power capacity. Directly, we can assess the flow rate with the probability, but we don't assess directly.
Okay. Which software or tools have been used for the quantitative geological modeling?
Almost all the tools that we're using, both geophysical and geological, are in-house tools that we developed in it's Python. For the geological modeling, it's the 3D fault modelings. We use a Python library called GenPy, but that we integrated directly in our code, so we don't use existing software. We do this mainly because that gives us the liberty to, we have access to the code and to do any modification, any implementation that we want.
All right. And the next question would be, how with such geophysical tools do you aim to delineate faults? What scale of faults are you aiming to characterize?
With the geophysics, to characterize exactly like the position of the faults, the best way to be fair is to use horizontal and vertical gradient of the Bouguer anomaly.
Yes.
Because that usually mark pretty well the faults. And in the 3D density models or any models, any large contrast of resistivity or density can help us define the fault. And then all all the geophysical model, we use them later for our characterization and geological modeling to characterize the resource more in detail. But for the fault itself, yeah, we use all the vertical and horizontal gradient of it.
Could you also discuss extension of the approach to an engineered or stimulated EGS setting?
What you mean for like an EGS?
Yeah.
Depends what you mean by enhanced geothermal system. Because if it's a system where there is natural hydrothermal system, but you want to stimulate a bit to increase the permeability in the forest and in the end the power capacity, the approach would be the same because you will still try to localize an existing hydrothermal system. And then if it's like more like on the side of the hot dry rock system, never really thought about it because we're focused on a hydrothermal system. I guess at least, yeah, if the system is completely dry, the resistivity won't really mark the presence of fluids, or except maybe like some brine in the basement. But you could still assess the thermal field and the heat capacity, the heat in place, and estimate the power capacity. You won't really use these. You won't really quantify any fluid composition porosity, but you could estimate the heat in place.
Then I have another question regarding the magnetotelluric data. Goes as the resolution of magnetotelluric data will be quite coarse. Do you think any deep ERT data will be better for shallow geothermal water?
Actually, we use a lot DMT for in the US where the resource is actually shallower. The resolution of DMT will and any geophysical method will decrease with depth. So the deeper the resources, the lower the resolution will be. So indeed, it's going to work better for like shallower system, but still a blind system. So without any type of surface manifestation. It's what we're trying to actually do in the US. It's blind system, but instead of being at 4,000 meters, they are like more around 1,500 meters to 2,000 meters. But yeah, in Europe, the temperature is the thermal gradients generally are all lower than the basement range, so the target are deeper. But obviously, it's going to work better shallower depth.
All right. What is the probability in your graph that you accept in order to proceed with drilling?
That really depends actually on the area, because in Germany, in the US, in France, it is different. The cost of drilling are different. The price that you can get for the electricity you're producing is different. So it really depends. In the US, we need quite high power capacity and lower depth target because the price of we can sell the electricity is lower. In Germany, the situation is different. The price is actually higher. You can get lower power capacity and a deeper target can still be economic. But it really depends on it's case by case, I would say. And we integrate this power capacity then in our like economic. If in the end it is based on the cost of the drilling, based on the price of the electricity, etc., if it's economic or not. And if it's not, then we.
Thank you. So the next one, the relations between geophysical properties and petrophysical properties are non-univoque. How do you deal with it, considering all the unknowns in the system and know well to calibrate?
It's a very good question. That's the part that is actually the most difficult. The thing is that we know that there is not a unique solution, so we try to we do multiple fits, run. Yeah, basically we do some type of Monte Carlo sorting. So for each cells, we'll try some combination of the parameters. The more parameters you want to fit, the more complicated the models and the result. But yeah, basically we do this Monte Carlo sorting of the parameters for its cells, and we keep the parameters that explain better the result of the geophysical models. And so that's why we have for each cell, actually, we don't have like a unique value, but we have a mean and a standard deviation for each cell of the model and for parameter that we want. Then in the end, if the standard deviation is really high, that means that we couldn't really find a solution that is coherent and that we can use. But if we have like standard deviation that is quite small, And that means that we manage in the end to explain the geophysical data and that we have results that we can kind of use. That's the difficult part because then any petrophysical law have their bias. Some are theoretical laws. Most of them are actually empirical or semi-empirical laws. So there is uncertainties on these laws. So yeah, that's the difficult part.
All right, so we have 6 more questions right now for the remaining 10 minutes. I'm gonna go ahead with the first one of them. What is the source for your heat flow data in Germany? Is it the German heat flow database?
Well, generally speaking, we use the flow world database. The data are from this world database. And then we also added information that we could find in the bibliography. That's data that we use really in the early process of our exploration to kind of do our regional screening. So it's all the data that I presented like in the first, except the fault model that we proposed. But apart from that, all the data about the fluid, the temperature, the lithologies, they were from the bibliography, from existing data. Then later, parallel to the geophysical acquisition, we also did a full survey to refine a bit the structural data available in the area, but this was not presented in this presentation.
Okay. Which tools can be used for this joint inversion of 3 geophysical data sets?
An internal code that we developed it's not public.
Okay, to go. Have you drilled wells and incorporated fiber to add higher vertical resolution component, ETS and DAS? Other work to prove commercial system connectivity?
The beginning of the question was about well that we drilled. We're planning to drill our first wells in the US probably end of 2025, beginning of 2026. We're actually in the process of planning the wells and the diagraphy that we want to do and the tools that we want to use and how we can incorporate all this in our workflow to refine our tool. But yeah, not yet for the moment, no wells.
All right. What tools do you use for joint inversion?
The same question that before is the internal code that we developed. Actually, the first version was years ago. There was publication. If you want to see about the tool, because it was developed in collaboration with universities in France. I think it's the paper Ars 2018, and this paper you can see if you want to have some ideas about the methodology. But all the code and the process is not like a software, it's our in-house tool.
We have one more, and that is how thick should a fault zone be in order to achieve good circulation of fluids? For example, 1 meter or 2 meters.
Actually, the faults are. I mean, we talk about crystal scale fault zone, so the faults can be like tens of meter, the size of the damage zone. But then, if there is a geothermal system along this fault zone, and you drill a well in the fault zone, probably actually you will intersect only few fractures, and it's only like maybe 4 to 5 main fracture that we produce, where you will have flow rate and you will produce. The main parameter is not really the thickness of the fault, but the permeability of the fault, and it's actually related to the connectivity of the fractures. But it's permeability reaches a certain threshold, you can generate free convection cells. No matter really actually the size of the thickness of the fault, but obviously the thicker the fault is, more fracture you will have that are connected, so the better the permeability would be. Just one last thing, yeah, again, what is important is actually the orientation to the stress field, because that is actually what will control if the fractures are open or not, and that will control the permeability.
All right. Thank you so much again, Agathe and Nicolas, not only for the presentation, but also for 30 minutes of answering all our questions. They sure have been a lot. So thanks again. And to every one of you, I'm wishing you a very nice start to this weekend. And yeah, have a nice afternoon. Thank you. Bye.
Thank you.